Have you ever stopped to think about how we can possibly know so much about these massive, complex things like the economy or the universe or public opinion just by looking at a tiny little piece? Well, today we're going to dive into that because we're talking about the statistical magic of sampling. It's this incredible idea that you can understand a whole pot of soup just by tasting a single spoonful.
And this really gets us to the heart of the puzzle for this explainer. We see this every single day with stock market indexes. I mean, the S&P 500, that's just a small slice of the entire US stock market. So how on earth can it be a reliable guide for the whole thing? The answer, it turns out, is all about the science of taking a good sample.
So to get this, we just need two basic terms. First, there's the population. That's the entire group we're interested in, the whole pot of soup, or in our case, all US stocks. Then there's the sample. That's the small part we actually look at, the spoonful, or the 500 stocks in the S&P. We study that sample to make a smart guess, an inference, about the entire population.
Okay, so you might be thinking, why not just study the whole population? Well, just imagine trying to survey every single telecom customer in the country about their spending habits, or analyzing all 6,000 plus stocks every single day. It would be insanely expensive and take forever. So sampling is really a practical trade-off. We give up a tiny bit of certainty to gain a massive amount of efficiency.
But here's the catch, right? That spoonful of soup might be just a little bit saltier or maybe less salty than the entire pot. That natural difference is what we call sampling error. And it's not a mistake, it's just an unavoidable part of the process. The whole goal of good statistics is to understand this error, to measure it, and of course, to keep it as small as possible.
So, how do we make sure our sample is actually a good one? How do we pick a spoonful that really truly represents the whole pot? Well, as we're about to see, the method you use to pick your sample, it's everything.
All right, the most basic way is a simple random sample. This is exactly what it sounds like. Every single stock has an equal shot of being picked, kind of like drawing names out of a giant hat. But a much smarter approach is stratified random sampling. With this method, we first slice our population into these meaningful subgroups. We call them strata, like different industries or company sizes. And then we take a random sample from each of those groups.
And this is where the technique gets so powerful in finance. Let's think about a bond index fund. The manager can't possibly go out and buy all 5,000 bonds in the index. No way. So instead, they use stratified sampling. They group the bonds by things like maturity, credit quality, and sector, and then they just pick a few representative bonds from each group. This ensures their smaller, manageable portfolio behaves just like the much larger index. It's a really brilliant and practical solution.
Okay, now we get to the secret weapon. There's this fundamental law in statistics that makes all of this work so incredibly well that, honestly, it feels a little bit like magic. It's called the Central Limit Theorem, and it brings this beautiful, predictable order to what seems like the chaos of random data.
So let's start with a population that is not a nice, neat bell curve, not at all. Imagine we're looking at corporate capital spending, which is uniformly distributed. That just means a company is just as likely to spend a little as it is to spend a lot. The graph for this looks flat, kind of like a rectangle, nothing like a bell curve.
Now here's what we do. We're going to dip into this weird flat population and take a random sample of, let's say, 100 companies, and we'll calculate their average spending. Then we do it again, and again, and again. We end up with hundreds of these different sample averages, so our focus shifts from the individual companies to this big collection of averages we just created.
And this is where the magic happens. When we plot all of those sample averages on a chart, something amazing takes place. They form a perfect, symmetrical bell curve. And the center of that bell curve, it lines up exactly with the true average of that entire weird population we started with. This is the Central Limit Theorem in action. It means we know the shape of our sample distribution, even when we know absolutely nothing about the shape of the original population.
Now, having this predictable bell curve is incredibly useful. It means we don't have to just give a single number as our best guess, which, by the way, is called a point estimate. We can do something much better. We can create a reliable range.
And that range is called a confidence interval. It's basically our best guess plus or minus a little wiggle room for where the true population average really is. So instead of just saying we think the average is 5.5%, we can say something much more useful, like we are 95% confident that the true average is somewhere between 4% and 7%.
It's a really honest way to show our estimate while also admitting there's some uncertainty from that sampling error we talked about. So how do we build one of these? Well, conceptually, it's actually pretty simple. You start with your point estimate. That's the average you got from your sample. Then you calculate a margin of error, which is basically a buffer zone that depends on how big your sample is and how much variety is in it. Your confidence interval is just that simple. It's your estimate plus or minus that margin of error.
But there's a really fascinating trade-off here. If you want to be more confident, let's say 99% confident instead of 95%, your margin of error has to get bigger. Your range has to get wider. So to be more certain that you've captured the true value, you have to give a less precise answer. It's like the saying goes, the surer we want to be, the less we have to be sure of.
So how do we get more precision? Well, the key is sample size. Just look at this table. With a tiny sample of just 10, our 95% confidence interval is massive. It's over 14 percentage points wide. But watch what happens. As we increase that sample size to 20 and then to 30, that interval shrinks dramatically. A larger sample cuts down our sampling error and gives us a much sharper, more precise estimate of the real answer.
All right, so we know how to do sampling the right way and build these precise estimates. But now we have to talk about the dark side. There are several really common traps or biases that can make our sample totally misleading and our conclusions just flat out wrong. First on the list is survivorship bias. This is what happens when we accidentally only look at the winners. Imagine a database of mutual funds that only includes funds that are still around today. It completely ignores all the funds that performed so badly that they went out of business. Any study using that data is going to make performance look way better than it actually was because it's only sampling the survivors.
Next up, data mining bias. You can think of this as torturing the data until it confesses to something. If you test 100 different things to see if they predict stock returns, pure dumb luck says that about 5 of them will look like they're significant. Data mining is when you only report on the 5 that worked and you conveniently forget to mention the 95 that didn't.
And this quote just brilliantly shows how absurd data mining can get. A researcher found an almost perfect statistical link between US stock returns and, wait for it, butter production in Bangladesh. Is there any logical economic reason for this? Of course not. It's a completely meaningless pattern that was found after the fact. Without a good story, a statistical link is probably just noise.
Let's hit 2 more really important traps. First is look-ahead bias. This is a tricky one. It's an error where a study uses data that wasn't actually known at the time. For example, using a company's final year-end accounting numbers to simulate a trade on January 1st. That's impossible because that data isn't actually released for weeks or months. Then there's time period bias. This is when your results only work in a specific era, like a stock-picking strategy that looked amazing during the 90s tick boom but falls apart in every other decade. So, here's the crucial takeaway. Sampling is this fundamental lens we use to understand a really complex world. From a small group of stocks to a political poll, it lets us see the big picture. But that lens can be distorted. We always have to think critically about how that sample was taken and what hidden biases might be twisting what we see.
And that leaves us with one last thought. The next time you see a news report, or read a study, or see an ad that quotes some statistic, I hope you'll have a new question pop into your head. What might be missing from this sample? And how could that change the entire story?
Thanks for watching.